Hello everybody, welcome to the World of Control channel. I'm Muhammad, and in this video I want to simulate a system of inverted pendulum on a cart with SIMSCAPE multibody in MATLAB. So let's get started. First of all, thank you very much that you are watching this video. Make sure that you subscribe to this channel because I will create a lot of videos about modeling different other systems and also designing different controllers about other complicated systems. So let's get started. First of all, I opened my MATLAB software here with the command of SMU. We can open a blank model of um, actually SIMSCAPE multibody model here. We have some details here that we do not need them, so I will delete them. And first of all, in our blank model, we have some default blocks here that we are going to use them to simulate our system. First of all, I want to introduce some default blocks here that are already in this blank model. We have a block named solver configuration. If we click on it, we can see some different settings here for our simulation. But for now, we do not need to change anything in this block for now. We have a world frame block here, so it represents our world frame, so we can use it as our world frame. And we have a mechanism configuration here that is showing our gravity vector here. That means that we have our gravity in the direction of z-axis and in the negative direction actually. And we can change the actually unit of our gravity here, that I do not change it because we want it to be a meter per second square here. And we have a linearization delta here that is 0.001, that we do not change it. We have some other settings here that we do not change them. So let's start our simulation. We want to simulate the system of the pendulum on a cart. First of all, I want to make a ground here. So if you click on this actually brick block here, we can open a blank, actually a brick solid block here that we can change it. It has some description here, so you can read and understand actually what does it do. And we have dimensions. We can see a coordinate system here that it means that we can change the actually value of these dimensions of this brick here. If I change one of them and click on apply and click on this update visualization here and click on isometric view, we can see that the value of x of this brick has been changed, and it is 10 meters now for now. So I want it to be, for example, 1 meter. I want, for example, 1 meter width and 1 0.01 meter, actually 1 centimeter, um, actually uh, the length of this ground in the direction of z-axis. Uh, we have other settings here. Export inertia. This inertia has some settings type based on density. We can change it to, for example, calculate from geometry, point mass, and custom here. If we need our actually solid bricks and solid links to be point mass, we can select this. But for now, because we fix our ground to the actual ground and the actual coordinate system, we do not change it and make it, for example, based on density. And for now, we make it, for example, 1000 density for it. So we do not change it for now. We have a graphic settings here that we can change it from geometry, marker, or none. For now, I will set it on geometry. We do not need to change this. And we have visual properties here that we can change the color of our links and our actually rigid bodies that we are importing to our model. So I will change it, for example, to blue color for now, and we can change the opacity of it. For example, if we set it as 0.1, we can see that it is actually like glass here, but we do not need to change it. So I will make it for now for 1. And we can actually use frames here to set some frames on it. If we click on this icon here, that we can see all of the frames that is attached to this actually ground and body here. For now, we do not need to change anything here. And we are going to connect the R frame that is here to the world frame here for now. Okay, now we are going to make our cart. If we actually push the control button and drag on the block, we can copy another block like that block for our system. Okay, I will go into the cart block here and change the values for the block here that we are going to have now. First of all, I want to make a prismatic joint between the bottom surface of this block here with the ground block. So I need a frame under this actually cart here. So I will go. I'm going to go to frames and click on the plus here, and we see that we have some options here that we can use. So I click on based on geometry, and I will click on the bottom surface here, and I click on use selected feature. So we can see that a frame is here now, but we have to pay attention to this fact that all of the joints in the SIMSCAPE multibody has to actually has to apply on the z-axis. They, for example, revolute joints rotate between z-axis of the frames, or prismatic joints can actually change the actually they can change the for example, distance between two rigid bodies along the z-axis. So we have to make sure that we are applying and using the joints between, or actually yes, between the z-axes. So we have to pay attention to this fact. So now we have to, for example, we want our prismatic joint to be along the z-axis. So I have to change the this z here to be on the x. And if I actually apply it, no, for now, let's make that very, for example, simple here. I will click on based on geometry feature, use this surface and use selected feature, and actually click on save here. Now if I show the frames attached to this body, I can see that I have a frame under this card here actually. Let's change the color to see the to see better the blocks and rigid bodies. Now we can see that we have a frame F here and a frame R here. Actually, we do not need the frame R, so we can unclick this option here to do not show the R frame here. I will double click on the Simulink model and I will write prismatic joint and I will import a prismatic joint. So I need to connect the base frame and the follower frame to my prismatic joint here. But I have to make sure that the both frames are connected to the base frame and follower frame of prismatic joint along the z-axis of them. So I will use a block called rigid transform here to rotate the frames that we have here. So if we see, we can see that we can rotate around the y-axis to make sure that the z-axis of the ground and the z-axis of our cart are aligned. So I will actually use the transform. If I click on it, we have a rotation and a translation. Now we want to use rotation. We have some options here that for now in this video I want to use the standard axis option here, and we can say that we want to rotate around y-axis about 90 degrees. And if we actually connect the base frame to the world and the follower frame to the B, now we can have our z-axis in this direction, and if we click on this and connect the base frame to the card and the follower frame to the prismatic joint, now we can see that our system is connected. Let's run the simulation to see if the appearance is good. Now we can see that we have our cart on our ground and we have a prismatic joint. Because the initial conditions are 0, we cannot see any movement for now. But let's connect our pendulum. So I push the control button and drag on our cart, and let's change the values and the magnitude of z dimension of our pendulum, for example, to be, for example, 4 meters. Now we can see that we have our pendulum, but I want to make it a little bit thinner and a little bit um, thinner in this way. Okay, we can see that we have our pendulum here. We do not change anything in inertia. For now, we assume that our actually materials are the same and we have the density of 1000 kilogram per um, actually per the volume. So uh, we need a frame here, but I need a frame in the middle of this line here to actually attach it to our um, revolute joint. So I will click, first of all, I will click on open and click on based on geometry and click on this line and select. We can see that we have a frame here, but we need it to be on the actually we need the z-axis to be on the negative direction of y. So we say that we want the primary axis of z to be aligned with the minus y here, and I will save it. Now we can see that we have a frame here. So I will rename this block to as pendulum. Actually, we have a frame on this surface of our card. So I will use frames, add a new frame based on geometry. I will click on this and use as selected feature. And actually, we need the z-axis to be on the direction of minus negative y actually. So I will change this to minus y. And now we can see that we have the F2 frame here. So we need to add a revolute joint, and we have our z-axis is aligned, so we connect the F2 as base frame and the F1 on the pendulum as follower. If I run the simulation, now we can see that we have our pendulum on the card system here. Let's change the color of our pendulum so we can distinguish all of the rigid bodies from each other. Okay, now we need to make it move. So I will add a force, external force and torque block here, and I want to apply a torque around the z-axis of our pendulum to see the movement of our pendulum. So we can see that we can apply force also, but for now, because I want to apply the force on the z axis of our pendulum, I will connect the F to this signal here that represents our actually frame of our pendulum, and I will import a signal generator. And for example, for now, I want to apply a sine wave torque with the amplitude of 0.01. But as you can see, we have some signals that the color of them are different from the original and ordinary Simulink signals. So we need a Simulink PS converter here to actually convert the Simulink signal to the physical signal actually. If I click on Simulink PS, we need to change some settings here. First of all, we need to uh, actually determine the unit of our actually input. So because it is torque, we need to choose it as Newton meter here. And also we have to use filter input derivatives calculated and change it to second order filtering. So our signal can have the first derivative and second derivative. So the Simulink can have all of the conditions that it needs to actually run the simulation. If I run the simulation, let's see why we do not have any movements here. Let's change it to 1. And if we run the simulation, okay, something is wrong. Let me see why we do not have our movement. Okay. Okay, this is z-axis, revolute joint, the z-axis on the frame 2 here. Oh, no, let me, oh, understood, I think I understand. We need to apply this rigid transform here. Let me see. Okay. Torque Z. If I increase the amplitude here, can we see any changes? Oh, yes. Our model was correct, but because of the amount of the density, we couldn't see the movement because our input was very low here. Now we can see the movement here, but for now, because I need to watch the movement of our cart, I want to reduce the density of these rigid bodies here and actually reduce the amplitude of our input to see the movement of our cart. It is not enough, so I will increase the amplitude of this. And now we can see that our pendulum is rotating and our cart is actually moving along this as x-axis that has the prismatic joint. For now, it's enough. Thank you very much. In the next video, I want to design a controller for this actual physical system. Make sure that you subscribe this channel because I will make other videos about other complicated systems. And thank you very much.